make sure to hit record. So yeah, starting this morning here on this last couple slides from chapter 9, I put up a set of review problems from chapters 7 through 9 to review for the midterm next week. So that's what we'll head into after wrapping up a couple slides here in the chapter 9 notes. But at the end of class on Wednesday, we were talking about the resonance in a molecule like benzene, and we're sort of noting that each of the positions of our vertices were carbon atoms, and then there's a hydrogen at each of these points too, so that we have 4 bonds to each of the carbons across the molecule. And the thing that we were pointing out is that we have 2 different resonance structures that we can write by moving these double bonds simply over to the other sets of bonds here in the molecule. And so what that means is the molecule really never exists as resonance structure A or resonance structure B. It always exists as the composite or the average structure. And so that makes these carbons across the molecule all the same type. These are both not quite double bonds, not quite single bonds, kind of right in between. So we have kind of the average of a double bond versus a single bond for each of the bonds across the carbon. And then the bond distances here are all equal. So the bond distance across the carbons, if we note that this distance here is equal to x, that's the same distance here because the bonds are the exact same type. And that's what we observe in the benzene molecules. All the carbon-carbon bonds have the same bond length because of this picture of what we call delocalization. So delocalization is the effect that we see in molecules that have multiple Lewis structures that are equivalent to each other. So the 2 resonance structures for benzene are both equally valid. They both look exactly the same as each other, just the difference is which of the bonds are making the double bonds. So the real molecule then never exists as A or B. In reality, it always looks like the average or the composite structure. And then we have a couple questions we can ask, like the ones on this page here. For benzene, like how many resonance structures does it have? It just has that one other resonance structure. So it just has that other resonance structure moving over to here. So that means it has 2 total resonance structures. So the resonance structure question would be how many total structures does it have? It's not asking like how many other structures could you write. We could write one other structure for a total of 2. What is the average bond order of the carbon-carbon bonds? There's maybe 2 ways to calculate this. I can think one of the sort of 2 bonds that are being exchanged, like the single bond and the double bond that are exchanging or averaging out. And I think it's pretty easy to see single and double averages out to 1.5. So that's one way to see how we get a 3/2 bond. Another way could be to think across the whole molecule is I could look and see that I have, 1, 2, 3. Let me go a different color so I know where I start. 1, 2, 3, 4, 5, 6, 7, 8, 9 total bonding pairs spread across now how many covalent bonds are there? Well, there's 1, 2, 3, 4, 5, 6 covalent bonds. So that's another way of seeing that you get a 3/2 bond. So you're just spreading the total of 9 bonding pairs of electrons across the accumulation of all the single and the extra double bonds, and then adding those up and seeing that the bond order is simply 3/2. Are all the carbon-carbon bond lengths in benzene equal? Yes, that's what we're talking about. That's the effect that resonance has, is it equalizes those carbon-carbon bond lengths due to resonance. And then how many electrons are in the delocalized pi system? The delocalized pi system are those electrons that are shifting around and moving. And so that would be, let's go back to the clean structure, but I think you can see that it's the 6 electrons that we're moving around. So it's just these 2 electrons, these 2 electrons, and those 2 electrons for a total of 6 for this particular molecule. So you'll see things like this. If you take OChem, you'll go into aromatic molecules, talk about all different kinds of things that are like benzene, similar to benzene, and have this, what we generally call aromatic stabilization energy due to having this particular count of delocalized pi electrons. Okay, so let's move into more of a review. Let's talk about a couple ideas for preparing for the exam. Obviously, like if you haven't done a lot of reading and you're stuck on a particular topic, going back and reading I think is helpful. I think it's sometimes helpful to spot read. If there's something you don't get, try to read that topic. If it's in section 5 of a chapter, you might have to read through section 1 starting, with section 1 to get the section in the middle of the chapter that you're stuck on. The one place I've always been at when I was a student was if I'm really stuck on a chapter or a topic, sometimes you just got to go to that first page of the chapter and just work your way through very meticulously, particularly focusing on the sample and practice exercises, hopefully by virtue of chapters 7 through 9 kind of being pretty similar to each other on the driving kind of topic of getting towards the idea of molecular structure and Lewis structures and 3D shapes, that I think we're reinforcing the material throughout the coverage of these particular chapters covered together. So hopefully you're finding that these chapters make a lot of sense, but if not, check out the sample practice exercises, the tutorials. If you haven't done those, you should still be able to access all the tutorials for practice if you're interested. Use the homework problems to help your understanding, but then quiz yourself at some point. So do a lot of quizzing this weekend if you haven't done a lot of closed book, closed note practice through daily quizzes, AI generated quizzes. Obviously we have the 2 practice exams. But make sure to take those as authentic practice exams, etc. And then as we start thinking, getting closer to the final, you can start thinking going through maybe a study session on chapter 1, doing some review of the sample exercises, a review of a quiz or 2, maybe a practice quiz or 2 or an AI generated quiz, and then see what you're struggling on and try to focus there. So try to focus on those topics that you're most struggling with. The Amgen Learning Center, how many of you guys have made use of this center? Fair number of hands. If you're looking for a place for help, the center has open hours for drop-in tutoring, Monday to Fridays, 4 to 8. There's some Sunday hours, 3 to 5 for chemistry. If you're in a bio class, there's some open hours for biology as well. So you can see other classes that are supported there if you happen to be in any of those other courses this semester. And I think generally they plan on expanding to some other courses in the future. But if you're in those courses like next semester, you might think you could make use of this learning center as well. And then this is just where the center is open if you just wanted to drop in and sit and study and maybe have a classmate or another student in 1210 that you can study with and ask questions to. So those hours are just where it's a place to go study without necessarily tutors available. So I just wanted to post those hours in case you were interested in those. This is posted on Carmen. And again, if you're looking for the slides on some review problems, these are in the lecture slide area, the chapter 7 through 9 midterm 4 review question packet in the lecture slides module. This question here, I wanted to throw this question in because this is kind of what the carbon-carbon single versus double versus triple bond question was getting at in the notes on Wednesday. If you recall, there was a question of what would the potential energy diagrams look like for a carbon-carbon single versus double versus triple. And I just wanted to show you an exam question that once was written. This was from 7 years ago. But the exam showed a representation of what the carbon-carbon single bond diagram looked like for the energy associated with forming and breaking that carbon-carbon single bond. So this would be the ideal carbon-carbon single bond distance. This is the carbon atoms separated, and this is the carbons that are then pushed together too close. And so then what would you expect the figure to look like for a carbon-carbon double bond? So I just wanted to show you that an exam question for this was just looking at us thinking, okay, the carbon-carbon double bond should be shorter, so this distance here should move over to a shorter distance, and then it should be stronger, so it should drop to a lower potential energy. And so that should look like figure C, where we're going to a shorter distance. So the distance here is shorter, and then the energy is lower, meaning that the energy to go from here to breaking the carbon-carbon double bond requires more energy. So the energy to go from the bottom of that potential well up to 0 or up to separation is our bond strength. And so that's showing you that the bond strength or the bond energy is increasing for the carbon-carbon double bond, because the more electrons we have as bonding electrons, the shorter the bond length, then the stronger the bond. So single bonds longer, weaker, double shorter, stronger, triple even shorter, even stronger is the idea. Okay, so I just wanted to show you a question that kind of fit into a topic from class last time. So from here, we'll kind of go back through chapter 7 and kind of work our way back through chapter 9. So we'll see how far we get in this packet today. My plan is to either continue into this packet on Monday morning. Again, we'll start up class 20 minutes early, as usual, before our exams on exam weeks. If we need some more problems or if you have particular questions, you can feel free to email me over the weekend. If you have questions today that you want to ask, feel free to, if you have questions after we work on a problem, feel free to let me know. But we're rank ordering here in this problem the effective nuclear charges in increasing order for electrons in the following subshells. So we have two different electrons in a sodium atom. We have the 1s versus the 3s of sodium, and then we have the 1s versus the 3p in chlorine. And so obviously the 1s electrons are the smallest electrons within these atoms. So those are the electrons that within those respective atoms are going to experience the greatest overall charge. So then if we're comparing sodium is element number 11, chlorine's element number 17. Chlorine has 17 protons, so the 1s of chlorine is sitting right on top of a much more highly positive nucleus. So that 1s of chlorine is going to get a lot closer to the nucleus due to that 17 plus charge, and it's experiencing that greater charge. So the greatest charge that we're going to see for any of these electrons is that for 4. So the 3p of chlorine, excuse me, not 4, it's 3. So 3 is the 1s. So the 1s of chlorine experiences the greatest charge for the chlorine atom, and it's greater than the 1s of sodium because 1s of sodium is only sitting on top of a plus 11. So the 1s of sodium sees that 11 plus charge, the 3s of chlorine sees that 17 plus charge. And so then 1 should then be next because our outer valence electrons don't experience that high of an effective charge. So the valence electrons are going to be blocked by the inner core electrons. And so the outer valence electrons don't experience nearly as high of an effective charge as those inner core 1s orbitals do. The 1s electrons are experiencing that full nuclear charge that nucleus has. And so that's why our electrons that are closest to the nucleus experiencing the greatest overall charge. And then the question becomes, well, between the two valence electrons for sodium versus chlorine, which one of those experiences the greatest overall effective charge? And then we just go to our left to right trend. So our left to right trend for effective charge is generally the trend for the valence electron. So we say our effective charge increases from left to right. So when we go from lithium to fluorine to neon, our effective charge is going up because the atoms are becoming smaller due to that increasing nuclear charge of the atom. The core count stays the same. So most of the nuclear charge as we increase from left to right is being experienced by the outer valence electrons. Same thing with sodium, that it has a relatively low, we reset our effective charge back to being relatively low with our alkali group, and then we increase then back from left to right. So our Z effective trend is that it increases left to right, but the key is that this left to right trend, this is for our outer valence electron. So we're talking left to right trends, top to bottom trends. We're thinking the outermost valence electrons trend for effective nuclear charge increases left to right. This is where we get our periodic behavior. This is why the left side elements lose electrons readily because they have a lower effective charge, and then the right side elements have a higher effective charge. They're smaller, they hold on to their electrons, takes more energy to remove their electrons as a result. And so then we get a slight increase of the effective charge from top to bottom. That's explained by the radial probability distribution functions. Even as you go to the 3s, the 4s, the 5s, we still have that probability of those electrons being relatively close to the nucleus and experiencing, therefore, on average, a slightly higher charge as you go from top to bottom. And so this probably doesn't come up all that often, but if we're comparing like lithium to sodium to potassium, we usually see a slight increase in the effective charge from top to bottom. But here we're just comparing the left to right trend. So sodium should be a lot lower than the valence electron for chlorine, but the key is that those charges are going to be nowhere near as high as the charges for the 1s subshells that are closest to the nucleus. Another thing we can break down is the Z effective for these atoms would go kind of in this order, that their 1s subshells experience the greatest charge, then the 2s, then the 2p, then the 3s, then the 3p. So as you go further away from the nucleus, your effective charge on average is dropping for a given atom. If you were to then compare this for something like titanium or look at something in the transition metal block and where you're continuing into the 4s and the 3D space, the 3D then comes next. So it goes 3D, then 4s. And so this is why, and this will be a later question in a slide or two on cation configurations. This is why it's something like titanium is going to lose that s electron first, the largest electron, the electron further away from the nucleus first upon ionization. So when we're looking at ionizing things like titanium or chromium, manganese in the fourth row of the periodic table, we're first losing the 4s electrons before we start taking the 3d subshell electrons next. But we'll look at those examples in a few moments. Let's rank some trends of size of atoms. And so we see a grouping of 2 anions and a neutral atom. And so when I look at, the first thing I kind of think about here is for sulfide and chloride, what do they have in common? What they have in common is that sulfide would have 16 plus 2, that's 18 electrons. Chlorine should have 17 plus 1, that's 18 electrons. So the 2 anions are isoelectronic. Chlorine's not isoelectronic. It only has 17 protons, or excuse me, 17 electrons, also has 17 protons. But for chlorine, it doesn't have that extra electron. As we add electrons to anything, we're adding the negative particle among a sphere of particles that are also negative that causes repulsion. So anions are always larger than their neutral counterparts. So if I'm comparing size, I know that chloride has to be bigger than chlorine just because adding an electron, a negative particle, into a sphere of negative particles is going to cause repulsion. Repulsions increase, we increase in size. And then what about sulfide? Does sulfide become bigger or smaller than chlorine? Well, sometimes we get a little confused. Like sulfur is bigger without a charge than chlorine, left to right trend. So if we're just comparing uncharged atom, we think left to right trend. But then also when we throw a negative charge onto sulfur of 2 minus, it continues the trend of being bigger as well. With the 2 minus charge, it's bigger than chloride by virtue of having fewer protons. So we have 16 protons, 17 protons for chlorine, the same count of electrons. So here we have spheres that each have 18 electrons, but one of them has 16 plus, one of them has 17 plus. The 17 plus is going to be smaller. So we look at when isoelectronic, we compare number of protons. So you look at the number of protons, as the proton count goes down, then the size is going to go up because you have less positive charge to pull the exact same count of electrons in for those isoelectronic ions. So chloride, sulfide, the connection we make there is not necessarily on this trend here. It's more on the size of the isoelectronic. We're comparing the number of protons. Trend 2 has all the ions that are isoelectronic with each other. So they're all 18 electrons. So 18 electrons for chlorine. Take 1 away from potassium, it's 18. Take 2 away from calcium, it's also 18. And its total electron count. So if you're forget, just look where calcium is on the periodic table. To get to a 2 plus means it lost 2 electrons. So we're down to 18. And so here we're just comparing the proton count, 17 for chlorine, 19 for potassium, and then 20 for calcium. So the one that should be the smallest here, what we're thinking is the proton count, because they all have the same number of negative particles. So it's like they all have 18 things that they're trying to pull in. One of them has a 20 plus, one of them only has a 17 plus. The 20 plus is going to win here in terms of pulling those particles in most closely, potassium, then chloride. And this is all based on 20 protons, 19 protons, and then 17 protons. So when things are isoelectronic, we're just looking at the proton count. Now, when we don't have a charge, we're comparing uncharged atoms, then we're just comparing we're just comparing the left to right trends, the top to bottom trends. One trend not shown here would be, like if I'm comparing the size of potassium, sodium, chlorine, and these elements relative to each other, the ranking I would make where these are all uncharged is that I know that potassium for sure is bigger than sodium, just from top to bottom. As you go from top to bottom, size increases. So I know K is going to be bigger than sodium. Let me move this over here so I have a little more room to write. So K is going to be the biggest compared to sodium. And then when I think of the size of chlorine, left to right size decreases because what we're talking about, the effective nuclear charge. The chlorine experiences a greater charge, it's going to be smaller, so chlorine is the smaller atom compared to sodium. So without charges, this is the kind of ranking I would get here. If I threw calcium into the mix, it becomes a little tricky to maybe get this comparison here, but for calcium, calcium without a charge would be smaller than potassium. So when we're comparing neutral atoms, we're just looking at left to right trends. We're just using the left to right trends of size, decreases left to right, increases top to bottom. Now, what about cations relative to their neutral counterparts? So cations, we're removing the negative particle that causes the repulsion in the size of atoms. So we're going to decrease size as we go to cations. So sodium should be the largest here. Sodium plus even larger. And then when I'm making the comparison between sodium plus and magnesium 2 plus, these both have 10 electrons. And this becomes now a question of how many protons do we have? 11 protons, 12 protons, same electron count, so magnesium is smaller. So it's all about trying to make a comparison. Uncharged atoms, left to right trends. Top to bottom trends, periodic trend for atomic size. Charged ions, we have to then think, well, what do they have in common with each other? Are they isoelectronic? If we then look at ions that aren't isoelectronic, if we're comparing fluoride to chloride, this just becomes a simple top to bottom trend. So if I'm then comparing 10 electrons to 18 electrons, this shouldn't be too tricky to see that this is the same reason that fluorine is smaller than chlorine, then fluoride is smaller than chloride. So it's the same basic top to bottom trend than if you're comparing, two ions to each other that are in different rows of the periodic table. The larger element is going to then have the larger negative ion when comparing ions of the same charge. So we can compare those just like we compare F and Cl. Move on from here. So ionization energy, so which ionization below requires the greatest energy to be absorbed. This is just asking which of those steps has the greatest magnitude of energy or is the highest overall IE. So these are all ionization energies that we're looking at. We can write the reactions too. Like the first ionization of sodium is sodium as a gas going to sodium plus as a gas plus an electron. I wouldn't necessarily worry too much about this, but just know that all of our electron affinities and ionization energies in chapter 7 were all for gaseous atoms, just so that we're comparing the atoms in the same phase as each other, so that we don't have any goofy solid phase or liquid phase differences between these reactions. The second ionization of sodium would just be sodium plus, losing that second electron to go to sodium 2 plus. So we can certainly write the reactions associated with these steps. Now that's going to have a tremendously high energy because now we're removing a core electron. The first one's not super high, the first one's relatively low. So the ionization energy of sodium, the first isn't too high because it's the leftmost element, low IEs. We increase ionization energy left to right. So that should be relatively low compared to most other elements. But the second step, this IE is going to be a lot higher. So this IE2 is going to be a lot higher than the IE1, that first step of sodium, just by virtue of removing a core electron. If I look at the first ionization of magnesium, it would be magnesium gas going to magnesium plus gas plus an electron. That this IE1 should be greater than the IE1 of sodium. So we can rule out that the IE1 of sodium here is the highest because we know the IE2 is higher than the IE1 of sodium. And then we also know that magnesium's IE1 would also be greater than the IE1 of sodium. So we can certainly rule out that the part A would be the lowest overall ionization energy. Then if we're choosing between B and C, which one of those is overall the greatest magnitude? Because they're both greater than sodium, but the sodium magnitude is going to be a lot higher than the magnesium magnitude, just by virtue it's removing a core electron. Magnesium is just removing an outer valence electron, which doesn't require that much more energy than sodium. So this question is a little bit tricky because we know both B and C are higher than A, but the key is that the step in B should be a lot greater than the energy in A, and the step in C is just marginally greater, maybe double. The energy of step B is probably about 10 times greater than the energy of A, so a lot greater for the second ionization of sodium. And in general, if you remember, the ionization of a core electron is always like off the chart in terms of ionization energies. We had mentioned before that each successive electron requires more energy to remove, and then the valence electron, or the core electron, once we start removing a core electron, takes a big jump, a big increase in energy. Now, what about potassium? Generally, IE trends from top to bottom is that IE tends to decrease from top to bottom. And this is a tend. Every now and then there is a slight increase because we have a give and a take between atoms become larger, the electrons further away from the nucleus on average, easier to remove as a result, but also the effective charge went up by a little bit. So the charges tend to, or the ionization energies tend to drop, but not by a whole lot as you go from top to bottom. And so the K ionization energy should be a little bit lower than sodium. Probably not much lower though, but just marginally lower. So the IE1 of D, this is probably what we could conclude to be the lowest IE1, or the lowest ionization energy of all these steps here would be D, and the greatest should be B. So if we're rank ordering, we're probably going D is the lowest, then A, for the first ionization of sodium, then probably that first ionization of magnesium, then the highest being the second ionization of sodium, that removal of the core electron. Electron configurations, this is kind of getting at that one thing that we were talking about for the relative effective nuclear charge for the different subshells of an atom. Helps us maybe understand certain cation configurations. But anion configurations are really easy. We're just picking up from chlorine being a outer 3s2, 3p5. So chlorine without the charge looks like this guy. And so then if we add the extra electron, we just go to a 3p6, add one more electron. So chloride would just be spin paired, all our electrons in the 3p subshell, takes on the outer configuration that's exactly the same as the argon configuration. And this is, of course, the configuration on top of the neon configuration. If we're thinking condensed configurations for these ions, like we did from chapter 6, but now for including ions. So anions just continue putting electrons into the subshells in the same order we were putting the electrons into in the first place into our elemental configurations. But then our cation configurations are a little bit more complicated. We have to think about which of the subshells is the largest, which has the highest N of the highest L. We might begin the picture with vanadium neutral. So the neutral vanadium atom, it's element number 23. So vanadium should have the argon configuration, followed by a 4s2, followed by a 3d3. Now, sometimes you might wonder, does this have an anomaly? I would generally not worry if any of these configurations were anomalous. And even if they were, you should generally come up with the same configuration anyways. Like vanadium really does have this configuration, so this is the actual configuration of vanadium. If for some reason you thought the 4s moved into the 3d subshell, then upon ionization to vanadium 2+, you're removing the 2 electrons from the 3d. But if you're picturing the correct configuration, then you should still remove the 4s electrons before the 3d. So the key is for cations, we're removing the electrons by rule, first from the orbital with the highest N value, with the highest L. Literally just ordered new tips for this pencil because it's why it's writing weird. But so the highest N with the highest L, this is just a fancy way of saying the largest orbital on average. And so the orbital size is just the whole N equals 4 shell is bigger than the entire N equals 3 shell. So this is just where we're thinking the 3s is going to be smaller than the 3p in terms of being smaller than the 3d. So this is going in order of size. And then we come to the 4s. So that's why we're going to remove the 4s first and then the 3d upon ionization. So vanadium 2+ should have a configuration of argon 3d3. So when we move to a 2+, we remove the 4s2 electrons. If we then move to a configuration for vanadium 3+, I then kick out one of the d electrons. So vanadium 3+ should be an argon 3d2. So argon 3d3 for vanadium 2+, and that's by rule. This isn't some anomaly. This isn't some goofy rule for just this atom. This is for all elements that we're going to remove electrons first from whichever orbital happens to be the largest. And then we're just taking note that sometimes this isn't what we thought of as the last orbital that we put electrons into our base configurations for neutral atoms. Okay, and so if we look at gallium 3+, it's right after zinc on the periodic table. So its configuration for, let's look at gallium neutral first. So the neutral gallium atom would be a 4s2 followed by a 3d10. And then followed by a 4p1. So again, it's right next to zinc, element number 31. And so 4s2, 3d10, 4p1. Then our electrons should be lost. Our 3 electrons we're going to have to lose to get to the 3+ configuration should be in order. The 4p should be lost first, and then the next 2 from the 4s. So we're losing the electrons in order of the highest N with the highest L first. So we take 1 from the 4p and then the next 2 from the 4s. And so our configuration should just be an argon 3d10. What about electron affinity? So electron affinity is the energy associated with absorbing an electron. So which atom releases the most energy? Electron affinities are often negative. There's some groups of elements that are positive, like the noble gases reset under the highest. They have the highest overall electron affinity. So our trend from left to right resets high with the noble gases, and then with the alkalis, we're decreasing more negative towards the halogens. And so the halogens are the most negative. So the halogen element here is going to release the most energy upon absorbing an electron. If we were to write the steps here, the steps would be the gaseous atom absorbing an electron to form the negative ion as a gas. I happen to have this memorized. Maybe you guys remember seeing this number. It's 349 kJs per mole. Just kind of to think of that magnitude, that it's negative about 350 kJs per mole. So just to get a sense that, like if you remember sodium being one of the elements that loses an electron with the lowest energy, it's about plus 500. So if you're just thinking energetically, sodium gas, 500 kJs per mole have to be absorbed for it to lose an electron. We get 350 back when we put the electron onto chlorine. That's still positive. So a slide in a moment or two is going to think back to, well, what's really the reason why we form solid ionic compounds predominantly? Why does something like NaCl predominate in nature and not sodium and chlorine? And the reason why is that once the plus and the minus form, they then have that strong attractive force. The electrostatic force of attraction of those ions is what drives the formation of ionic compounds. Now, if we compare these reactions above, I don't know if I need to write all these, but they would have the same basic reaction to form a negative ion from the gaseous atom. And then the highest here should be argon. In fact, we don't even put a number on these. I'm not even sure they've been measured because it's so unlikely that an argon can accept an electron. So argon would have the highest overall electron affinity for this group of elements. And so then from left to right, we're decreasing towards the halogens. I wouldn't get too caught up on, there's a couple of like peculiar grouping trends from left to right where like the NS2 group, like the beryllium group, tends to be a little bit positive or not as negative as you might expect from left to right because it has to put an electron into a higher energy subshell. And then the like nitrogen groups, not as negative as you might have expected because it has to spin pair an electron. So there's a couple deviations, so we don't get a straight decrease from left to right. I wouldn't overly concern yourself with memorizing or knowing or expecting that nuance to be tested. But if you're looking at ionization energy trends too, we generally say ionization energy, removing an electron, that energy increases from left to right, but there is also a couple configuration issues there too, where the boron group is a little bit not as high as you would expect because it is removing an electron from a larger orbital, so it's a little lower energy than you might have expected left to right. And then removing an electron from like an O atom, and the oxygen group is also not as high as you would expect because you're dissipating the pairing energy that was associated with pairing the electrons in the first place. So you see a couple configuration issues with IE, but we're generally just trying to make sure you know IE generally increases left to right. Electron affinity decreases more negative towards the halogens, resets with the noble gases being the most positive. Okay, so this is the slide I was kind of talking about on the kind of link between, you know, that it's not really that sodium plus is so much more stable than sodium. In fact, it takes energy to create the cation of sodium. If we're looking at forming, you know, from magnesium and chlorine, why would that form magnesium chloride as the solid ionic compound? And you can see the reason why here is really just that the energy, the relative enthalpy or the energy of formation of magnesium chloride is more stable. So that's why any reaction takes place is for that reason, is it's leading towards something that's more stable than some other alternative. And so what happens for magnesium, in order for it to form magnesium chloride, is it has to turn into a gas. That takes energy. The chlorine bond has to break. That takes energy. We have to ionize 2 electrons off magnesium. That takes a lot of energy. Like magnesium 2 plus, like it's so funny, magnesium 2 plus isn't exactly more stable than magnesium. It's just once it forms, it leads to something else that can then lead to the greater stability. What makes magnesium 2 plus so special is that it, when paired up with chloride, when it gives its electron to chloride, it can then experience that electrostatic force of attraction. So this force of attraction here is that electrostatic force of attraction. It's the attractive nature of the cations and the anions. It's like the negative of the lattice energy. So we get this really from the two anions and the cation pairing up and forming the solid ionic compound drives the formation of magnesium chloride to be more stable due to just how negative or exothermic that particular step is. So lattice energies are all positive. If you take a solid ionic compound, break it apart into its gaseous ions, that's a really positive value. We rank order that. That'll be the next question. We can rank order lattice energies. That is, the charge of the ions goes up, the lattice energy goes up. Takes more energy to separate. As the ions become smaller, when we're comparing plus and minus, smaller is better because the ions can get closer, it takes more energy to separate. And so we can rank order lattice energies very well, but we're seeing here that this is when you take the two ions, or you take the cations and the anions and you allow them to experience that electrostatic force of attraction to form the IC, that's really exothermic. That's the driving force. That's why this compound, magnesium chloride, is more stable than its elements. And then it would be more stable, like this compound with a 2 plus and a minus, presumably is more stable than if you just left magnesium with a plus and change the charge on chlorine. Like if you said, why not magnesium 3 plus? Takes too much energy to create magnesium 3 plus. Why not stop at magnesium plus? Well, magnesium plus is just a little bit smaller than magnesium. What if we go to magnesium 2 plus? It's a lot smaller because we've lost the 2 outer valence electrons. So there's a lot of interplay between what are the best things that these ions can do to then experience the greatest overall attractive force, the greatest overall negative lattice energy, in consideration of how much energy it took to create those ions in the first place. Notice that the electron affinity is negative, but it's not that negative. So we don't get that much energy back. It's not just the energy back from the electron affinity, it's the attractive force. It's the electrostatic force of attraction that drives these ionic compounds to form. I would not expect a math problem here. We have asked math problems before. You can throw all the numbers together. It's a nice Hess's law example. I never even went through one. You can see some old exam questions on my daily quizzes if you want to see an example of those. But I wouldn't worry about the math here, more of just the idea of which steps are positive and why are they positive. Like magnesium solid to gas is positive because anything like water solid to gas, we have to have ice absorb energy to turn into a gas. Anything has to absorb energy to go solid to gas. We have to absorb energy to break a bond. Bond energies are always positive. So it takes energy to break the bond in chlorine. It takes energy to ionize electrons. You get a little energy back when you put them onto something that's like a halogen atom. So you can understand why these steps are positive versus negative and then their relative magnitudes. Okay, so then another type of question on lattice energy is just then like rank ordering lattice energies for different compounds. And so the thing I look at compounds first is I compare their charges. So I have a 2 plus, 2 minus for both of these compounds here. And then the question becomes, well, when the charges are the same, well, let's rank order then which ones are smaller. The smaller the ions, the closer the charges get, the harder they would be, the more energy it would take to separate them. We're just looking at our kappa Q1, Q2 divide by D. If I can make the distance closer together for the ions, the magnitude of attractive force, now think about how we have plus and minus here. The energy of attraction, this is one of those negative potential energy questions where there's an electrostatic potential energy between the plus and the minus that's negative. Think about the magnitude of that energy. Think about not the sign of it, think about the absolute value of that attractive force. As the ions become closer together, the energy of attraction goes up. The magnitude of that attractive force goes up, so it's going to take that much more energy to separate those ions. So it's MgO here, having the smaller set of 2 plus 2 minus ions that has the greater lattice energy. And then it's plus minus, so I gotta be careful to make sure I'm comparing the same charged ions. When we're looking at ions that have the same charges, the smaller set of ions will win out and have a higher overall lattice energy. So it's grouping A that would have the highest overall lattice energies. And then I can even rank order that NaCl is going to have a lot lower lattice energy compared to calcium sulfide, because when I'm comparing the charges too, I can make this comparison really easily, that if I increase the magnitudes of charge, then I'm going to increase the energy attractive force as well. So I know that the 2 plus 2 minus ions should both be a lot higher than the plus 1 minus ones. And they're a lot higher by about a factor of 4. So the size trend has a small impact on lattice energy. It'll take the lattice energy of NaCl versus KBr probably from like 800 to 750 kJs per mole. So a small difference of lattice energy between NaCl and KBr. MgO and CAS are probably on the order of like 3,000 to 3,400, and their difference is probably like 100 or 200 kJs per mole. So a small difference. The size trend has a a couple hundred kJ per mole difference, maybe a 200 to 400 kJ per mole difference, but the charge magnitude has multiples of orders of increase of lattice energy. So I can rank order all of these, that the lattice energy to rank order all these would be KBr, the smallest, then NaCl, and then the larger calcium sulfide, the highest here being the smallest, 2 plus 2 minus MgO. So I could rank order all 4 of these as well if I wanted to. Because we know the 2 plus 2 minuses should all have a greater lattice energy than the plus 1 minus ones. Among boron, carbon, nitrogen, oxygen, fluorine, which atom when bonded to fluorine forms the most polar bond? So the most polar bond would have the greatest difference of electronegativity. So our electronegativity is increasing towards fluorine in both directions. So fluorine's the most electronegative atom. My most electronegative atoms are, I've mentioned this a bunch of times, just when I see NOFCl bonded to anything but themselves, I know that's going to be a polar bond. You can also maybe think sulfur is fairly polar, bromine's fairly polar as well. Just about anything involving these atoms here is going to make for a bond that's certainly polar. So fluorine, when bonded to boron, the element furthest away from it in this grouping, is going to give that bond the greatest difference of electronegativity. So it's boron that has the greatest electronegativity because it has the greatest difference of electronegativity. And electronegativity, if we inspected the chart, which I don't have on the slide here, but if you look back at the chart, it's a regular increase left to right with no periodic breaks of inconsistency. And then if you get all the way to like lithium fluoride, this is where you're getting to ionic. So if you go metal, non-metal, this is something we'd call ionic. This frickin' pen. So we call that ionic. I don't know if I look for any particular difference of electronegativity to call a bond ionic versus polar, covalent versus nonpolar, but I would call an F2 bond, when it's the same atom bonded to itself, this has to be nonpolar. Whenever the electronegativity difference is so small, like a CH bond's not very great in terms of the difference of electronegativity. I don't even like to look at the difference. I just kind of look at this as being, it's none of the elements I kind of think about as being the most electronegative. So their difference is going to be pretty small. This is probably a nonpolar bond. But then when I think of taking any of these atoms paired up with anything but themselves, I don't even care to look up the electronegativity difference. I know it's going to be a polar bond. Even like the goofy NCl, because N and Cl have the same electronegativities. NCl3, this molecule that looks like this, has lone pairs on all the chlorines, that molecule there turns out to have a dipole moment. It's like 0.6. How can it have a dipole moment if the bonds were nonpolar? So this molecule here is polar because this bond here, even though the difference of electronegativity looks like it would be 0, and it should be nonpolar if you think of the electronegativity difference being really small, somehow this molecule ends up having polarized bonds. So the way I would kind of think about electronegativity is anytime you take these elements paired up with anything but themselves, the bond's going to be polar. Don't even think about needing to know what the electronegativity differences are. And then when the elements are further away, or when you take something like fluorine that's the most electronegative paired up with something far away from it, it's going to be a really polar bond. Start thinking metals, nonmetals, I don't even care so much about electronegativity differences for those two. If I take a metal, nonmetal, it's going ionic. And I don't want to be too nitpicky on, well, do I need to know an electronegativity chart to know the difference? I'm just thinking metal, nonmetals, those are going to their full charges. And then that one region of my iPad, I don't know, maybe my iPad's broke, I don't know. No one's by, I can't seem to write on it. But lithium plus ionic, so LiF ionic, KF ionic, KBr ionic. I don't even care what the electronegativities are. I'm just thinking metal, nonmetals are ionic, just like we've thought about from the very start of chapter 2. Can we judge a Lewis structure question like this one here, so let's just look at the question. It says, which Lewis structure below is the dominant Lewis structure? That's kind of a fancy word for the best Lewis structure for the molecule NH2COOH, which has the name carbamic acid. And we're told to consider formal charges. And so I have 3 different Lewis structures here to kind of choose from. And the way I might use formal charges is just, well, let's take a look at the formal charges of all of our atoms. And so hydrogen's really easy. It's just 0 in all of these. So nothing fancy going on with hydrogen. Let's look at nitrogen next. So the nitrogen should have 5 electrons, and it has 1, 2, 3, 4, 5. So it's a 5 minus 5. So that's 0 in this structure. So for formal charge, you're thinking, how many valence electrons does nitrogen have? It has 5. And then I'm thinking, well, if I have an atom that looks like this, that has 5 electrons around it, I just break the bonds in half, count the electrons, keep the non-bonding pair on nitrogen. So I keep the non-bonding pair on nitrogen, give it the other 3 electrons. That's just a neutral nitrogen atom. The oxygen up here should have 6, and it has 6, so that's neutral. Carbon should have 1, 2, 3, 4, and it has 4. Carbon has a valence count of 4, has 4 electrons around it. So that's a formal charge 0 carbon atom. Oxygen here, this should have 1, 2, 3, 4, 5, 6, so that's neutral as well. So all the atoms in A look to be formal charge of 0. That looks to be pretty good. So I'm thinking probably A is going to be the answer, but let's make sure that we get something worse in structures B and C. So in B and C, the thing that I kind of noticed right off the bat is that they all still satisfy the octet rule. So all these Lewis structures, it's not like the octet rule is being broke. Carbon has 8 electrons, nitrogen has 8, O has 8 in all these structures. And the octet rule question is just look at the entire electrons around an atom. So those are all 8. But the formal charges are going to be different. So nitrogen's formal charge here only has 4 electrons. So that's a positive formal charge. Oxygen here has 7 electrons. So that's 6 minus 7. So that's a negative formal charge. This guy here is still the same. So that's still neutral. So I'm plus and minus on my N and O. And now it seems like why would N go positive? Like you may think, well, nitrogen's less electronegative. Maybe this is good. Maybe I want the structure to do this. But the best Lewis structure is going to minimize the magnitudes of formal charge when all else is equal. And all else being equal, what we mean by that is that we're still satisfying the octet rule equally in both structures. And so this is going to roll B out because we've now maximized our formal charge. So I'm just curious if it works there. It must be something in that spot on the iPad. Excellent. Anyways. For structure C, why is this one probably bad? Well, nitrogen goes back to neutral, so we're back to neutral for this nitrogen. We're still at negative for this oxygen, same as the other one. That's a 6 minus 7. And then our count here for this oxygen, that this one should have 6, it only has 5. And so again, you're just breaking the bonds in half. Whoops. So if you're not sure, and if you're getting confused on how I'm coming up with these counts, just break the bonds in half, count the electrons, 1, 2, 3, and then 4, 5. So that's how I come up with that count of 5. So that gives me a charge of plus 1. So plus and minus, again, not 0 across the board, so we can rule C out as well. So A, we're looking at which of the structures has the lowest overall formal charges. Now, what I can do is it's okay in some structures to try to think, can I put the more negative charge on the more electronegative atom? But it's going to have to be when all else is equal in some other ways. Let's look at a structure like the molecule NCO. This is unbelievable. NCO minus. Might go to the chalkboard. I do have another, I put it back in the bag, another tip for this stupid pencil. Let's go to the chalkboard for this. So for NCO minus. And so the Lewis structures for this, we just go back to our count, 5 for nitrogen, plus 4 for carbon, plus 6 for oxygen, plus 1 for the negative charge. So that's 16 total electrons. And so when we're just putting these in this particular order here. So nitrogen to carbon to oxygen. And so if I start with my lone pairs like this, like we usually would with a Lewis structure, that's all my 16 electrons, so no lone pair for carbon. And so then we're thinking, okay, let's make a double bond, because carbon's formal charge is +2 without making a double bond. So let's reduce that formal charge, make a double bond over here, lose that electron pair. And so now we're at plus for the formal charge of this carbon. So let's make another bond, and the question becomes, do I make a bond here and go triple? So my options could be making a triple bond here. And let's, for that case, move that electron pair over to here. So that reduces this formal charge down to 0, but now oxygen's formal charge is negative in that structure. We can then have a structure where we go N double bond carbon, make the double bond over here, and then leave that as it initially was with the double bond. Now this makes this formal charge 0, carbon's 0 in both, but then it makes this formal charge here now negative because this nitrogen has 6 electrons. So that nitrogen goes negative in its formal charge. Oxygen 0, carbon 0, carbon 0 here as well. And so then the other possibility is, well, why don't we do the carbon, why didn't we just make the triple bond over here with oxygen instead? Why don't we just leave nitrogen single? So I think you can get to these structures just from thinking about, well, what are the range of possibilities for a molecule like this? These are the range of possibilities, and the formal charge for oxygen here would be plus. Why plus? I have 6 minus 5. Oxygen should have 6 electrons around it. It only has 5. Nitrogen only wants 5. Now it has 1, 2, 3, 4, 5, 6, 7. So I have a 5 minus 7 for plus 2. I'm sorry, for 5 minus 7 for minus 2. Now, which of these structures is by far the worst? This one for sure is really bad because we're putting a positive charge on the more electronegative atom at the expense of a really negative charge on a non-electronegative atom. So this structure here is by far the worst. But now do you see here, I'm choosing between two structures that put the negative charge either on the N or the O. Okay, but the key is that I'm not choosing between a structure like in the one on the screen where I have zeros across the board and then a negative on the O. So what makes structure B bad that we crossed out is it doesn't just put the negative on the O, but it puts a plus on N. It's maximizing formal charges. These formal charges otherwise are the same. So the Lewis structures, I would say, are identical other than in where the bonds are being put on the molecule, but the more negative charge would be best. If I'm choosing the best Lewis structure, I'm going to choose the one that puts the more negative charge on the more negative atom. So you just have to be careful to think, I'm using the rule putting more negative on the more electronegative atom because I had another Lewis structure to choose from that had the same set of formal charges overall. If I could have somehow made a 0 across the board, now you may be sitting there thinking, is anybody thinking, well, why not do this? Is anybody thinking that? And why would this be bad? We can't expand the octet of carbon. So we can't we can't add that extra electron onto carbon. So I can't put 10 electrons around carbon by rule. So I can't expand the octet of an atom in the second row, and I really should rarely do it for third row too, but for third row elements, maybe you can expand their octets within some Lewis structures, but for something like NCO-, we certainly can't expand beyond 8 electrons around carbon. Okay, so I think... All right, so this part of the video is me talking after class, after I wrote out a few options that I had been writing on the chalkboard, was having some issues writing on my screen in class today on this slide. But for NCO-, we came up with these 3 Lewis structures. I think a test question for this would probably likely show you the 3 Lewis structures and ask you to evaluate which one's best. We can even maybe consider one more Lewis structure that looks something like this. So imagine a test, said you have structures A, B, C, and then D to choose from. I think we can rule out D because it violates the octet rule. We can't expand the octet of carbon. Would have been nice if we could because it makes 0 formal charges all the way around, but we can't make 0 formal charges all the way around at the expense of the octet rule. Structures A through C at least all obey the octet rule, but then we're just putting too high of magnitudes of charge in C, so that rules C out. That's the worst option among A through C. The expanded octet's probably even worse than C though. And then B and A are similar in that they have -1 formal charges on one atom, but if we can choose the negative formal charge to be the more electronegative atom, that would be better than putting the negative charge on the lesser electronegative atom. And so the key would be just make sure to compare what you can compare. You know, if you're comparing two structures that otherwise are the same, put the more negative charge on the more electronegative atom, but don't, in the case up here, go with the structure that puts a negative charge on O at the expense of maximizing the formal charge on some other atom. So that's why we rolled out B up here in the first question on this page. That will be a good stopping point for today. Leaves us some good problems we'll look at on Monday. I did put a key for all these up, so if you want to see a key for these problems, a key for the problems, you can find those on Carmen if you wanted to look at those problems, but there's a ton of practice problems. But we'll wrap up with the quiz, and I'll see you on Monday. Have a good weekend.